Measures of occurrence. Measures of occurrence want to answer what, how many or how much, when, and to whom. There are two main types of measures of occurrence that we use in epidemiology. Incidence measures the new cases of a disease. Commonly measured incidences are cumulative incidence, the incidence density or rate, and incidence odds. And the prevalence, which is the total number of cases present in a population at a given moment of time, a snapshot of the population at a given moment of time. Common prevalence is calculated are point prevalence, period prevalence, lifetime prevalence, and prevalence odds. Measures of association seek to establish whether there is a link between the properties which differentiate the subgroups in a population and the occurrence of an event in the population. Measures of association are good to compare an index condition to a reference condition, but you must specify this comparison clearly. There are two types of comparison. You can compare two quantities in terms of the absolute difference between them, and you can compare them in terms of the relative difference between them. Absolute difference measures are the subtraction of the measures of occurrence among exposed minus the measures of occurrence among unexposed. For example, the incidence rate difference is the incidence rate of exposed minus the incidence rate of unexposed. In absolute difference measures, when exposure has no effect on the outcome, an absolute difference is zero. Whereas relative differences are ratios in which the measures of occurrence are among the exposed are divided by the measures of occurrence among the unexposed. And you can have an incidence rate ratio where you divide the incidence rate of the exposed by the incidence rate of the unexposed. In relative measures, when the exposure has no effect on the outcome, the relative difference is 1. Now, often when we read epidemiological papers, we come across three common ratios. The rate ratio, which is the incident rate for the exposed divided by the incident rate for the unexposed, the risk ratio, and the odds ratio. These three are often called relative risk. It is important to pay attention to which type of relative risk you wish to calculate, for they are each different. So, one of the most important things to remember when you're doing quantitative research into associations is that association does not imply causation. Causation is in fact very difficult to establish. One of the things you have to consider is confounding, which occurs when a third variable is associated to the exposure and to the outcome. Controlling for confounding should be a central concern when measuring association. But bear in mind that even if all confounding were to be eliminated, association still does not imply causation. As an example, let's consider Jon Snow's cholera outbreak. In this imaginary scenario, imagine that he had not correctly hypothesized that the source of water was related to the cholera outbreak. Instead of collecting each household's water source, he had measured other aspects of the health of the population. He would find that urine high in salt among family members of cholera was associated to the incidence of cholera because the water supply was contaminated with sewage. Thus, he would find a very strong association between a urine that is high in salt and cholera, which might lead to the conclusion that a diet high in salt causes cholera. Another non-imaginary but quite real example is the relationship between low birth weight and smoking. So among the whole population, it has been well established for a number of years that maternal smoking is strongly associated with low birth weight and increased mortality. Among low birth weight babies, however, babies of mothers who smoke have much lower mortality than babies of non-smoking mothers. So, does smoking cause a protective effect for low birth weight babies? The answer is no. Many factors affect a baby's mortality, not only smoking. And other factors leading to low birth weight among babies of non-smoking mothers have a larger effect on mortality than smoking. And healthy babies of smokers might otherwise have been born of normal weight were it not for smoking. However, if you don't measure potentially confounding factors, you cannot control for them. This highlights again the importance of a good design. In the previous example on low birth weight and smoking, it's important to consider before you start the study that there are many ways of thinking of this association. For example, smoking could be associated to low birth weight which would in turn be associated to increased mortality, or smoking could be associated to both increased mortality and low birth weight. These are 7 of the potential diagrams showing the potential sets of associations just between smoking, low birth weight, and mortality, along with some unknown causes. It is important to consider this before you begin your data collection. A classic example of the importance of considering all the sources of confounding and accounting for them before you begin your study is exemplified by Simpson's paradox, which is a strong case of confounding by indication. Here are the results of a study which measures the effects of a treatment on people with kidney stones. Now, as you will see, people are divided by those having small stones and those having large stones. People having small stones always have more success with treatment A. People with large stones always have more success with treatment A as well. However, if you don't separate people by the size of their stone, but rather analyze them together, you can see that treatment B comes out as a superior treatment. Now, this is an example of confounding by indication, and it's caused because patients with large stones are more likely to receive treatment A, and patients with small stones are more likely to receive treatment B. However, if you don't consider this before you start your study, you will not know this, and you will only see that treatment B is superior, which in this case is clearly the opposite of what we're observing with the patients. To help design your quantitative study, directed acyclic graphs are very useful tools. They help avoid confounding by presenting all the known relationships between the variable in a graphical layout, and tools such as Daguerre, available at daguerre.net, can help you build your own DAG. In conclusion, having quantitative data does not automatically mean that you can meaningfully interpret them. The quality of your quantitative research depends in large part on the congruence between the problem you seek to address and the design you use to address it. That is all for the basis of quantitative research design. In the next section, we will cover the basis of statistical analysis.